All right, well, welcome back, everyone. Welcome to the very last lecture of this little seminar series. Hope you've been enjoying it so far. I know I have. And sorry about the delay today. Just like usual, some technical difficulties with getting the recording started. So yeah, before I start, as usual, I'm just going to do a very quick recap of what we did last time. So last time we looked at the analysis of variance, or ANOVA. We started out with the one-way ANOVA, and we looked at different things called sums of squares, which explained different parts of the variation in our data. And we used those to formulate the ANOVA test statistic, the F-test. And we saw that that was what we called an omnibus test. So we only looked for general differences between means of our different groups. But we also looked at post hoc tests, which allowed us to compare the individual pairs of means between our different groups. If our general ANOVA came out to be significant, then we would go ahead and run our post hoc tests. And we also looked at a very simple introduction to the factorial ANOVA, so looking at different combinations of more than one group. Okay, so the title of today's lecture is Putting It All Together. What do I mean by that? So far we've seen a number of very simple but very useful statistical tools. So we've seen we've seen some general measures of uncertainty, of central tendency. We've seen some methods of doing kind of an initial data exploration before we actually do any formal statistical testing. We saw our t-test, we saw our one sample t-test, our independent samples t-test. We saw linear regression, and we saw, of course, last week our ANOVA. But as something I've tried to stress before is that the statistical analysis isn't something that you should be thinking about after you've collected your data. This is something that you should be thinking of right from the very beginning of your study, right when you're coming up with the study idea. And if you do that, you can actually save yourself some pain later down the line. This is something that I know from experience, from what I've seen other people do with their experiments. There were things that maybe could have been done better and would have saved us a lot of trouble later down the line when we actually perform the statistical analysis. So today I'm going to talk about a couple of things. I'm going to talk about what sorts of things should you look at or consider before you actually start your experiment or before you start collecting your data or whatever you might be doing. And I'm also going to look at, okay, once you have data, what should you be doing before you start any formal testing procedures? And so today it's going to be a slightly shorter lecture. I have only 30 slides today, but maybe I guess that worked out better because we had a little bit of a delay. So I was hoping to have a little bit of a longer question period at the end, but maybe we won't have enough time, but we'll see. So the first thing I'm going to start out with is something that I've had several questions about over the course of this seminar series, and that's looking at sample size calculations and power calculations, which really are the same thing, but just kind of looking at different elements of your study. So a sample size calculation is a very common thing that you would do when you're undertaking a new research project. So this is something you might do when you're writing a grant application. It could be something that you do in a pilot study, or it could be even something that you do for the proposal of a PhD thesis. So the point of a sample size calculation is to allow us to get a reasonable idea of how much data we need to collect. And by data, I mean just how many individuals we need to sample in our study to have a high probability of detecting some association, if such an association is truly there. And Oh yeah, yeah. So we're looking at like a minimum sample size to get this association with a high probability. But conversely, we can also look at kind of a maximum sample size that we might want to collect. So you might think, okay, well, shouldn't we be collecting as much data as possible? Well, in general, in statistics, that's true from a purely statistical standpoint. But realistically, collecting more and more samples, it can cost time, it can cost money, and it uses up resources. And you can sometimes find that if you're lucky enough that you can collect a lot of samples, that as you collect more and more samples, you get diminishing returns on the precision of your estimates relative to how much time and effort you've spent on collecting those samples. So sample size calculation can do both of these things. It can look at the minimum number of samples you need to get reasonable estimates, but it can also look at, kind of a maximum. Though I would say you're very lucky if you end up in the latter scenario where you have to actually find out where you should stop taking samples. Most people are in the scenario where they need to find the minimum amount of samples they need to collect. So in a sample size calculation, so the minimum sample size you need is going to depend on some parameters. But the thing is that we don't know the true values of the parameters. These are things that we're actually trying to estimate from our study. So what we have to do is we have to create kind of a set of what-if scenarios. We have to think about reasonable values of the parameters and plug all these values into our formula and see what the minimum sample size comes out as. So we can look at multiple scenarios. The point is we don't know the true values of these parameters. And there may be research out there already which could give you a reasonable idea of what parameter values to try. But in general, it's just something that you have to sort of guess at, give some reasonable values, and you want to give a range. Okay, so just a quick reminder. You might remember I showed you this table a few lectures ago. So what we have is in the columns, we have the truth. So we have one column for if the null hypothesis is false. So that would mean that there's something interesting to find in our data. And another column for the null hypothesis being true. There isn't anything interesting to find in our data. And as our rows, we have the different outcomes of our statistical test. We have one for rejecting the null hypothesis. Okay, we declare a significant result. And as you can see, I changed the terminology from this. I say, do not reject the null hypothesis. So we do not declare a significant result. So the main thing that we're interested in, usually, is this thing right here, correct rejection of the null hypothesis. So there is something in truth to find in the data, and we do declare a significant result. And if you think of taking multiple samples, like a large number of samples from this same population, and doing the statistical test over and over again, sometimes you're going to get a correct rejection, and sometimes you're not going to get a correct rejection. But the proportion of times that we do correctly reject the null hypothesis is called the power of the study. And this is sometimes written as 1 minus beta. We'll see why that's the case in a few slides. But we generally want this power to be as high as possible. But there's kind of a catch here, because there is a very, very easy way to ensure that the power is as high as possible. And that would be to just declare every single association significant right off the bat, no matter what you see. By doing that, you would guarantee yourself 100% power. Because every time you have So the reason why you get 100% power is because every time you have two variables that have a true association, you're just going to be declaring significance no matter what. But the catch is that you're also going to have a large number of what you call type 1 errors. So in the case where the null hypothesis is true, you would also be declaring significance for all those tests as well. And so we don't want that to happen. If you remember, this type 1 error was kind of the equivalent of sending sending an innocent person to jail. We don't want that to happen. So it's kind of a balance between getting a high power, but also not having too many type 1 errors. And so our rate of type 1 error is called alpha. And this alpha, the type 1 error rate, actually turns out to be equal to whatever significance level alpha we choose to do our statistical test at. Okay, so there are a few basic elements that would go into a sample size calculation, and there are more that I'm not talking about here. But so the first thing you have to do is you have to determine the type of test you're going to perform. So are you going to do a t-test? Are you going to do an f-test? That sort of thing. So in order to get a formula for the required sample size, we sort of start with the final test statistic that we would have and look at its distribution under the null hypothesis and the alternative hypothesis. And we would work backwards from that final test statistic to see what our required sample size is. So the basic important items that go into this sample size calculation are, okay, firstly, the power we would like to achieve, the type 1 error rate, the effect size. So if you're thinking about the difference between two means, it would be how big is the difference between those two means, and the variation in our data. So how much within group standard deviation do we have? And so we would want to choose kind of a reasonable range of values for each of these and see how our required sample size changes. So I'm going to illustrate a sample size calculation through the independent samples t-test. Okay, so if you remember back to our independent samples t-test, we're interested in comparing the means of two different groups. So just group 1 and group 2, which we denoted by mu1 and mu2. So we're interested in seeing if the difference between those groups is equal to 0 or if it's not equal to 0. And so I'm just going to call the difference between the two means delta. That's just a common sort of notation we use for that. So remember, these are population quantities, and I guess in the case of the sample size calculation, they're supposed sample size, they're supposed population quantities. So we don't really know the true values of them, but we're just kind of giving reasonable estimates. The standard deviation in each group we assume to be sigma. So remember, one of the assumptions in the t-test is we have the same standard deviation within each of the groups. So we just call that sigma. Assume we want to have a power of 1 minus beta. So again, this is something that we choose a priori. And it's very common to choose a value of 0.8. So you see that often in grant applications. It's just kind of a standard that people use. You want to see at least a power of 80%. Assume we have significance level alpha, as usual. Then the minimum sample size in each group actually turns out to be a very nice formula. So it involves this mean difference on the denominator. It involves the standard deviation, and it also involves these Z statistics, which are, I guess they're not statistics, they're the tail probability of the standard normal deviation. So in the case of Z 1 minus alpha over 2, that's just the probability under the tail to the right of the value 1 minus alpha over 2. You have one of those for the significance level and a second one of those for the power. And so just by plugging this all this into the formula, then you get the required within group sample size, kind of like the minimum within group sample size to make sure that you achieve a power of 1 minus beta and type 1 error rate of alpha. So here's what this power calculation looks like in terms of the t-statistic distributions. So on the left side, in the red distribution is the distribution of the t-statistics that you would get under the null hypothesis. So this is exactly the same thing that we would be looking at when we do our t-test. We would be comparing our observed t-statistic to this red distribution. The blue distribution, however, is the distribution of t-statistics that we would get under repeated samples from our population if our population was under the alternate hypothesis, so the kind of the supposed values that we came up with. So as you can see, the traditional, the null hypothesis distribution is centered around 0, and the alternate hypothesis distribution is not centered around 0. So anyway, if we look at these two thresholds that are plotted on this graph, these are the critical t-values. So if you were doing this experiment and you wanted to test at level alpha, then these would be your two thresholds. If you got a value beyond this threshold, then you would reject the null hypothesis. If you had a value to the left of this other threshold, you would also reject the null hypothesis. And if you fell between the thresholds, then you would not reject the null hypothesis. So if you imagine, so remember that we're assuming that this blue curve is the true distribution. So if you look at the proportion of times under this blue curve that we fall to the left of this critical value, well, that would be kind of the proportion of times where we make a type 2 error, so we know that the alternate hypothesis is true, but we did not find a significant result. So we call that beta. And the area under this curve to the right of this critical value is when we correctly reject the null hypothesis. And so that's what we call the power. So we want this power to be as big as we can reasonably get it. So yes, as I said, we have our red distribution, which is distribution of t-stats under the null. So alpha is the probability of our type 1 error. So here I'm doing a two-tailed test, so it's really alpha divided by 2 on either side, on either tail. And so if this null hypothesis were true, then falling to the right of this critical t-value or to the left of the other critical t-value would represent a type 1 error. And if we fell in between the two thresholds, then we would also, we would correctly not reject the null hypothesis. So sometimes we call the area under the curve between the two critical values the specificity. So the point is that this blue curve, where that's located relative to the red curve, depends on 3 things. It's going to depend on the effect size. So if you see a large difference between the groups, then that distribution is going to be pushed over to the right, which means that the power is going to be increased. And if you have a small variation in your data, then the same thing is going to happen. The blue curve is going to be pushed to the right. And the same thing is also going to happen if you have a large sample size. Blue curve gets pushed over to the right, this beta probability shrinks, and your power gets bigger. Okay, so I'm going to do a very quick example. So let's say we're doing an independent samples t-test, and we want a power of 0.8 and we want to test at significance level 0.05, which would imply type 1 error rate of 0.05. Okay, so we can just choose, we can do one of two things. We can choose a reasonable range of values for this mean difference and for this within group standard deviation sigma. But turns out that there are many pairs of values of this mean difference and standard deviation that will lead to the same power. And basically what we look at instead is this ratio between them. So just the mean difference delta divided by the standard deviation. So basically you're just looking at how big that mean difference is relative to the within group standard deviation. And so I'm going to try 3 different values for this D. So 0.5, 1, and 1.5. So 0.5 would mean that the mean difference is only half of the within group standard deviation. 1 would be the mean difference is equal to the standard deviation, and 1.5 would mean the mean difference is 50% larger than the within group standard deviation. So, and as it turns out, these are actually all very large effect sizes. 1.5 is something that you would be very lucky to see in your data. Here's a quick illustration of these different effect sizes. So here we have our 2 groups that we're comparing in the t-test. So we have the red group and the blue group. And so on the left side here, we have a comparison. Well, okay, so in all of these cases, the mean difference, the difference of the means between the 2 groups is the same. And in fact, it's equal to 1. So the mean difference is equal to 1 here, the mean difference is equal to 1 here, and likewise here. But the difference here is that in the first scenario, we have a small within group standard deviation. In the second scenario, we have a kind of medium within group standard deviation. And in the third scenario, again, the same difference between the means, but a larger within group standard deviation. Well, so when you go to calculate your effect sizes, you can see we have exactly the effect sizes that I am considering in this power calculation. So the first one has a very strong effect size of 1.5. And so the point is here that because there's a very, very apparent difference between these 2 groups, you know, the difference is large relative to the within group standard deviation, we're not going to need a very large sample size to actually detect this association. Whereas if we look on the other side with the effect size only 50% of, with the mean difference only being 50% of the within group standard deviation, okay, you know, when you plot it graphically, it still does look like there's a difference, but in order to actually find a statistically significant result, we're going to need a much larger sample size to be sure of that difference. So here's a nice plot, which I'm going to show you how to do later on in the lecture. So we have, on the horizontal axis, we have the power of our independent samples t-test, so ranging from 60% all the way to 90%. And on the vertical, we have our total sample size. So that's the sample size taking both groups into account. As you can see, it's exactly as I described in the last slide. So the first one, is sort of gray curve, is the smallest effect size. So if we wanted 80% power, we would just follow this up to the curve, and we would see that we would need about, I guess that's 125 samples total, so about 62, 63 samples per group. Well, if our effect size jumped up to 1, then we would need a much smaller sample size to get the same power. So in this case, we would only need about 25 total sample size. And if we had a very large effect size of 1.5, then we wouldn't need a very large sample size at all to get our 80% power. So that was just a sample size calculation for the independent samples t-test. So if you want to do a calculation for a different kind of analysis, say an ANOVA or linear regression, multiple regression, then you're going to have to redo the sample size calculation. We can also take other items into account in our sample size calculation, so we can have observations like, say, repeated measures where we don't have independent observations. We can have correlations between different variables in our study, and we can also have confounding factors, so factors that are going to affect the sort of relationship between variables and make an apparent relationship appear even though there isn't a true relationship. But for most standard statistical tests, a very good software choice, which is also free, available on both Mac and Windows, is called GPower. And so that's the software that I'm going to show you at the end in the tutorial today. And there are tons of online resources available as well. If you just do a Google search for power calculation and whatever statistical test you want, you'll probably find an online sort of calculator that you can use to do that. And when we get to very, very complicated analyses, sometimes what we do is we do a simulation. So we would simulate data under our alternative hypothesis and then do our statistical test. We would just do this over and over and over again and see how many times we would reject our null hypothesis, and then we can get an estimate of error from, an estimate of power from that. All right, so I'm going to move on to randomization. I'll probably just do one big question period at the very end this time. Okay. So I'm going to define what we call a confounding factor. So now we're getting into something that's very common to study in epidemiology, what we call causal inference. So assume that we're interested in studying the relationship between some variable x and an outcome variable y. So basically any of the tests that we've done so far fall under that scenario. You know, our independent samples t-test is looking at x would be your two groups and y would just be your continuous variable of interest. The point is that in many observational studies, so I'm not talking about experiments, I'm talking about observational studies where you just get the data and you see what you can find. There are often factors that exist that can induce a spurious association between x and y. So an association could appear even though there is no true association between the variables x and y. So let's say, I've drawn here what's called a causal diagram. So essentially what we're looking at is we're looking at the effect of x on the variable y, which I represent by this arrow. And we have an additional variable which we call c, which affects both x and y. And so this variable c is called a confounding factor. So basically, you know, it can affect both x and y and make it seem as if there's an association between the two. My favorite example would be something that we use in biostat and epidemiology very often, where if you're looking at x is yellow fingers and y is lung cancer, so you're looking at the relationship between yellow fingers and lung cancer. Well, if you were to do this association, you would probably see a pretty strong effect, right? Well, as you all obviously know, yellow fingers aren't going to cause lung cancer. There's a confounding factor. So if you're a smoker, so if this C is just presence of smoking, then that's also going to give you a higher probability of having yellow fingers, and it's also going to give you a higher probability of developing lung cancer. So that's a really well-known example, that kind of a silly one, but really does a good job of kind of explaining the point of why confounding factors are important to take into account. So the good thing is that dealing with a confounding variable is quite easy. All you have to do is adjust for it in your model. So if you're doing linear regression, you could include that confounding variable as an additional predictor in your model. If you're doing an ANOVA, something I didn't talk about, but something that you can look up if you're interested, it's called analysis of covariance, or ANCOVA. It essentially allows you to run the ANOVA as you did before, but while adjusting for additional variables. And so you can include your confounding variable as an additional variable in this analysis. Okay, so this whole talk about confounding factors was more in the realm of observational studies. So in observational studies, these things are usually outside of our control. So these things might be like age, sex, socioeconomic status, and smoking. These are common things if you're looking at humans. But as many of you are doing, you're looking at experimental data rather than observational data. And so the good thing about experimental data, the main advantage, is that we do have control over which individuals fall into our different experimental groups. But we have to be careful, because if we don't do a good job of doing this assignment of individuals into the groups, we can actually end up with confounding by study design. And so the way we typically avoid this is that our assignment of our individuals into experimental groups or into treatment groups have to be randomized. And so if we randomize, then we absolutely know that no external variables are affecting the assignment of the experimental condition. And so theoretically, in this case, we wouldn't actually have to adjust for anything. I put theoretically in for a reason, because, in statistics, there's always the theoretical and there's the realistic. So realistically, when you have a small sample size, randomization might not actually be enough. So you could end up with what we call imbalance in the experimental groups. And this imbalance would arise just by chance. So you did randomize, so you know that there weren't external variables that affected the assignment of the treatment. But with a small sample size, you can still end up with a kind of imbalance just by chance alone. So for example, if you have two groups, let's say you have a treatment group and a control group, and you're looking at some clinical measure in mice, you could, just by chance, have ended up with a lot more male mice in one group than the other group. And so even though there was nothing actually caused that imbalance, this imbalance will still introduce bias into your results. So there's a few things that you can do when you do this randomization and find imbalance. So if you see imbalance before you even start your experiment, the good thing is you can actually just redo the randomization and see if you get a better balance. It's perfectly okay to do that. But in many cases, there are certain things that you can't actually see until you've actually collected your data. And so if after you've collected your data, you find that you do not have balance between your two experimental groups, then you will have to include that variable in your analysis. Even though you did randomization and technically that's supposed to take care of things, you're still going to have to do that adjustment. Randomization is also a very, very important thing in mitigating technical factors. So when you're working in the lab, there are lots and lots of things that can have impact on the measurements that you take. things that aren't really familiar to me. I don't spend any time in the wet lab, but things that you're probably familiar with. So one thing that we see very often in statistical genetics is that when you process samples in different batches, you can end up with a batch effect. So if you run a bunch of samples in one batch and then run another bunch of samples in a second batch, you can see that the kind of maybe the mean of your measure is going to be slightly different between those two batches. Even things, you can see effects for things like the day that the samples were processed. So if you did a whole bunch of samples on a Tuesday and then a bunch of samples on a Friday, sometimes you can see a slightly different effect or a slightly different mean between those 2 days. And even the lab technician that happens to be doing the experiment can have an effect on your results. So maybe one day you have person A running the experiment, and maybe on another day you have person B doing the experiment, and person B happens to be a little bit hungover that day, and so they don't do a very good job. So the point I'm trying to make here is that it's always a good idea to randomize over absolutely everything. So, don't do all of your treatment samples on one day with one person. Don't do all of your control samples on another day. Just sort of mix and match like all your samples at every single step of your experiment. And by doing this, you can really save yourself a lot of trouble later on. Okay, so I'll give a quick example of a batch effect from something that I've experienced in my own research. So I've looked a lot at DNA methylation analysis. So I looked at data from the Illumina 450K chip. So what we're looking at is just levels of DNA methylation at various loci throughout the genome with respect to disease cases and controls. It's a very specific disease, but I can't say exactly what it is. So just imagine we have two different groups, and we're just comparing, say, average methylation over the entire genome with in the case group and in the control group. So in the 450K platform, you can run batches of 96, up to 96 samples at a time. However, it's well known that there's a technical artifact, that there's a very strong batch effect between different batches. And so there are normalization methods that exist. So say you take all the samples from one batch and you can sort of like push everybody up a little bit and push everybody down in another batch so that all the distributions sort of line up as they should. But if you don't have a good study design, then you're basically stuck. The normalization isn't going to do anything for you. So here's an example of what I mean. This is something that I've seen on 3 separate occasions. So this is a very, very real problem. So let's say I have my 2 batches, and I have disease cases and disease controls. And I put all of my cases in through one batch, and I put all of my controls in through another batch. So the problem with this is we have what's called confounding by design. So when we go to do our analysis, we actually cannot separate out the batch effects from the case versus control effects, because every single case is on the same plate and every single control is on the same plate. And even if you do normalization, this isn't going to solve the problem, because normalization is going to try to get these the average methylation from these 2 batches to be, I guess, the distributions of these methylation of these 2 plates to be equal. But by doing that, you could be kind of erasing the true biological signal that exists between the cases and the controls. So normalization doesn't do anything to solve this problem. So a much better study design, which would be to mix and match the cases and controls in your different batches. So you have, some cases and some controls in the first batch, and some cases and some controls in the second batch. So then when you do the normalization, you're kind of taking into account both cases and controls when you estimate this within batch variation, and it's just going to make it so that you don't have this confounding by design. All right, so that's a very simple example of something where the researchers had maybe taken a little more care in the study design. They would have ended up with a much stronger analysis than they actually ended up with. Okay, so everything up to now was what you should be doing before you have your data, before you do your experiment. So now I'm going to very quickly talk about things you should be doing after you've collected your data, but sort of before you start your statistical test. So one thing that you'll have to do is create a data set. So you take all of the data from your experiment and you might get it into something like an Excel file. Well, this takes a very, very long time. Do not underestimate how long getting your data into a proper data set and getting it nice and clean is going to take. It really does take a long time. But one of the biggest mistakes I see in data sets that I receive from my collaborators is they won't be consistent when they're entering the data. So things that I see is that you'll see factor variables, so say like a variable like male and female, won't be written consistently throughout the document. So for example, you might see male written all in lowercase letters, and for another individual, you would see a capital M for male. Or you might see spaces between some words. You might see spaces at the end of words. You might see typos, that sort of thing. The point is that when you go to read this data set into statistical software like SPSS, SPSS is actually going to think that all of these things are separate groups, when in reality they should all be in the same group. So you would have to go back and fix that. So it's best to just, right from the beginning, be as consistent as possible with the way you label everything, just to save yourself a lot of hassle when you read everything into your software. Another thing that I see is when you have dates listed in the file, see dates listed in like 3 different formats. So just make sure that all the dates are all in exactly the same format. Another thing is sometimes you see flags for missing data. So if an individual has a missing observation, I've seen in the same file, I've seen an empty cell to represent a missing observation. I've seen NA, like in capitals, NA with a slash, little NA with a slash, little NA with no slash. And so this is exactly the same problem with the factor variable labels. So that when you read these into your statistical software, it's going to think that these are all different things. So you just want to make sure you're very, very consistent with everything as you're entering the data. And lastly, you want to make sure that the variable names you have are very informative, so there's no ambiguity as to what the variable is describing. And something that I sometimes see but don't always see is that it's always a good idea to have a separate file where you describe the different variables and what they represent in a little bit more detail than you can get from the variable name. It can be very, very helpful, especially if somebody else is going to look at your data set. Okay, so again, before you do your statistical test, you want to think about your confounders. So this is very, very important if you have observational data. So you want to start by thinking, okay, what variables could affect the outcome variable? So if we go back to our confounder, we want to think, okay, are there any variables out there that could affect the outcome variable y? And if you can identify some, then, well, you can also think about whether they'll also affect x, because that's the only way that they would actually be able to confound your results. But often what people do is a term that we use in our department is you make a confounder soup. So you just take all your possible confounders and you just throw them into your model. And then you don't worry about whether or not they're actually associated with the x variable or not. You just play it safe and put everything that you can into your model. Of course, that's not always the best idea, especially if you have a small sample size. You would have to really think about what the most important variables you would need to adjust for are in your analysis. But the good thing is, I mean, the thing to remember is that you should always err on the side of caution there. So yeah, if you have a randomized experiment, great. But as I mentioned a few slides ago, you should always still check for balance of the variables in your different experimental groups. Because you might still have to do adjustment. Even though randomization is supposed to prevent you from doing adjustment, you still might have to do some adjustment nonetheless. And also, going back to our first lecture, you want to think about who or what the study applies to. So you think about, so if you're talking about people, what population are you describing? Can the results from your study be generalized to the entire population? This is a little bit more difficult when you're thinking of things like cell lines, but in the case of things like people, this is something that's really important to think about. Are my results generalizable? Okay, so when it comes time to actually run the test, well, first off, you have to choose the test that you're going to do. So start out by thinking very, very carefully about what research question you want to answer. So you want to make sure that you're choosing the correct test. And so for example, if you're interested in comparing two specific groups, then don't do an ANOVA, because an ANOVA is giving you kind of that omnibus test. Make sure that you understand what the test you're running is actually doing. Understand the population parameters that you're investigating, and understand what the null and alternative hypotheses are. And if you don't quite understand something that you're doing, don't be afraid to look it up or just to ask someone, because it can be very dangerous when you get people that are running statistical tests that they don't really understand and don't know how to interpret properly. One of the most important assumptions you should be thinking about is the independence assumption. So if you have something that's like repeated measures, where you take like a baseline measurement and then a post-treatment measurement, you want to compare baseline to post-treatment in, say, different treatment groups. The baseline and post-treatment measurements are definitely not independent. So you have to go to different analysis, like in the t-test, you can go to the paired t-test. So that's one of the most important assumptions that you should think about. And as for the other assumptions, well, check as many assumptions as you can. It's especially true in linear regression when we look at those residual plots. So you just want to make sure that your assumptions are somewhat met, or if the assumptions aren't met, then you want to justify why you're using this analysis. So for example, if you're looking at your ANOVA and you don't think your variables are quite normally distributed, well, as I had mentioned, ANOVA is actually quite robust to departures from a normal distribution, so you could still sort of justify using an ANOVA. It's just you have to really think hard about all the assumptions that you're making every time you do a test. Okay, so the very last thing, so we've already talked about how you actually do the test. So once you've run your test and you have some results, you should always be taking a moment to just stop and thinking, okay, do my results make sense? So you can start out by looking at things like effect sizes. Okay, does the estimated effect size actually make sense given my units of measurement in the data? So if your variable ranges from 0 to 10 and your effect size is 200, then that's a good sign that something's gone wrong with your analysis, or maybe there's an error in your data set or something like that. So just by looking and seeing if your results actually make sense given the units of measurement in your data, it can give you it can be a very good way of finding problems in your data set or in the procedure of your analysis. If you get a relationship between two variables that was completely the opposite of what was expected, well, it could be something that's true. You never know. But when that does happen, often what you can do is you can double check to make sure that things were coded correctly in your analysis. So it's very common in statistical software if you have two groups that you're comparing that you treat it as a binary variable. So one group you just assign a 1 to, and the other group you assign a 0 to. But if you reverse what groups you call 1 and 0, then the effect is going to flip sign. So if in one case it's a positive effect, if you flip those 1s and 0s for the different individuals, then the effect size is going to be negative. So if you see a relationship that's exactly the opposite of what you expect, again, go back into your data and make sure that your groups are defined properly. And go into SPSS and make sure that it's interpreting those different variables correctly. Okay, are you worried about an outlier? Well, as I said in a previous lecture, generally you have to have a very good reason to get rid of an outlier where you think that there's actually something wrong with that measurement. But one thing that you can do if you have an outlier and you're kind of worried about it is you can run the analysis twice, once with the outlier and once without the outlier. And a lot of the time what you see is that when you run the analysis again without the outlier, you see that the results don't even change very much. And so in that case, you wouldn't worry too much about the outlier. And I know I'm going to sound like a broken record here. I keep talking about this, but the final model that you choose should only be based on good statistical practice and making sure your assumptions are reasonably met. And you should never, ever choose your analysis based on the one that gives you a significant result. I can't stress that enough. Okay, so the take-home message from both this lecture and from, I guess, the entire lecture series is statistical analysis is super, super important. And I'm not only saying that because that's my profession. It's something that's absolutely true. And you really need to start thinking about it right from the moment that you start thinking about whatever study you're interested in doing. These days, it's very, very, very easy to run these statistical analyses, as I've shown you in SPSS. However, you still have to make sure you actually understand what the test is doing. You don't have to understand all of the math that's going on underneath, but you still have to understand what it's actually testing, and you have to understand how to properly interpret your results. And one thing I just want to leave you with is that it's always a good idea to consult a statistician in your project. Even if you think that it's going to be a fairly simple statistical analysis, you can always come and talk to a statistician just for an hour or something like that and just describe to them what you're doing, and they may have some advice for you or something you might have missed in, say, your experimental design. And you should do so right at the moment that you start thinking about your study. Don't wait until you're done your experiment. Don't wait until you've collected your data. Go to the statistician right away. And there are a few examples where if people had come to talk to me right at the very beginning of their study, they could have saved themselves some pain later on. And to leave you with a quote from Ronald Fisher, who's a very, very famous statistician. To consult the statistician after an experiment is finished is often merely to ask him to conduct a post-mortem examination. He can perhaps say what the experiment died of. So maybe a little bit melodramatic, I admit, but I still agree with the point. It's really always a good idea to come talk to a statistician before you actually start your study. All right, so once again, I think I'm going to wait on the question period for the very end. I'm just going to very quickly show you how to run GPower to do a simple power analysis, and then we'll do our question period. So, GPower, so as I said, this is free to download. I would strongly recommend using this if you don't have an alternative. So in GPower, you have all these options that you can look at. You can look at different types of tests like t-tests, f-tests. So I'm going to show you how to do what we talked about in the lecture today, the independent samples t-test. So once you have the test family chosen, you can choose your statistical test. So I'm going to look at the difference between two independent means, two groups. So that's exactly our independent samples t-test. And as you can see, you can do all sorts of different power analysis. You can do a priori, so that's the standard one where you're just starting out. You haven't done anything yet, you haven't collected data yet, and you just want to see, okay, how many samples should I collect? But you can also do things like a post hoc analysis where, okay, you've already got all of your data, and so your sample size is already determined based on the study that you did, and you want to see, okay, what would our achieved power be? I'm just going to show you how to do the a priori one. And so all you do is you just have a set of parameters that you can sort of play around with, and you can choose a one-tailed test or a two-tailed test. So I'm going to do a two-tailed test. You enter the effect size D, so that's exactly what I showed you earlier. That's the difference between the means of the two groups divided by the within group standard deviation. So I'll do an effect size of 0.5. You can choose your type 1 error probability, or alpha, the significance level, 0.05, and you can enter the power that you want to achieve. So I'm going to set that equal to 0.8. And then this last thing is called the allocation ratio. So this is just how many samples you have in each of the groups. And so if that's equal to 1, then that just means you have an equal sample within the two groups. So once you have all that entered, then you can just click calculate, and it's going to give you a nice plot like I included in my presentation. But more importantly, on the right side, it's going to give you some output parameters. So it's going to give you the sample size in the two different groups. So in this case, if you had an effect size of 0.5 and you wanted at least a power of 0.8, then you would need 64 samples within your two groups. So if you change this to something like 1.2, so that's a very strong effect size, then you would actually only need 12 samples within each of your groups. And one thing that is very useful is if you click on this button at the bottom here, X, Y plot for a range of values, you can make a very nice plot like I showed you in the presentation. So there are a few things you have to play around with here. So I'm going to make it so that my power ranges from 0.6 all the way to 0.95 in increments of 0.01. And then I'm going to choose 3 different curves on my plot just by changing that value there. And you can change the different effect sizes that each of the curves represents. So I'll say I'll start at an effect size of 0.5 and in steps of 0.5. So that's going to be the same thing as we saw in the lecture where we saw 0.5, 1, and 1.5 as the 3 effect sizes that we consider. And so I'll leave my alpha error probability as just 0.05. And so if you draw the plot, it'll just automatically give you this very nice plot with a separate curve for the 3 effect sizes and our power on the horizontal and our total sample size on the vertical. And once you have this plot, then you can actually save it. You just click on File, and then you can save this this XY plot, and you can save it as a PDF or a PNG or whatever you want. So it's just something that's very, very useful if you want to do your own power calculation. All right, so that's the last thing I wanted to show you. So I guess we can go to our question session. And the questions that you ask can be related to today or related to anything that we've talked about in the lecture series.
One of the microphones that we speak up. I have a question in the last plot. You showed the total sample size. Does that include the control cases together?
So the total sample size is the sum of the two. So if you have a total sample size of 20, that would mean 10 in each group.
Although, but it's still possible to have double amount of controls versus cases.
Actually, things are going to change if you have double. So if you, let me illustrate here. So that's where this allocation ratio comes in. So right now I have effect size of 1.2 and I have 12 in each group. But if I change this twice as many, then I think this should change. You have 9 and 19. So you would actually have to have a larger sample size in that case overall. Yeah. So I mean, so the question was in animal models, what sort of effect size could you consider to be a strong effect size? That's something that I've really...
So, like never do 60 for animals.
Oh, of course not.
So, maybe that effect size wasn't realistic.
Yeah, so the point is that, yeah, when you do an animal model and you have a much smaller sample size, that's okay, but you have to kind of assume that the effect size that you're looking at is going to be very, very strong. So that's especially true when you have 5 samples in each group, when you're doing something that's just not realistic to get, dozens and dozens of samples. You're just going to have to live with the fact that you need a very, very strong effect size. Otherwise, you're just never going to be able to detect an association. Yeah. And that's really context dependent. In an animal model, it might be very common to see a very large effect size, but in other, maybe observational studies, the effect size might be really, really, really small. For example, if you're talking about, if you're looking at SNPs, single nucleotide polymorphism, sometimes the effect size for a single SNP can be very, very, very small. So yeah, it's really, really dependent on the context of the data that you're looking at. Yeah, so the question was, what about in TCGA and publicly available data sets where you don't have information on what days the samples were processed and that sort of thing? Yeah, that is kind of a tough scenario, because if you don't have that information, then you're probably just going to have to take a leap of faith, I would say. But it's something that you should be very clear about in your description of your project. You should say, we acknowledge that we do not have this information, but it could affect our analysis. But if you do have that information, then it wouldn't be that difficult to.
Food delivery actually.
I'm sorry?
Food delivery.
Oh, can you wait for a little while for the next?
Okay.
Yeah, but if you have that information on like the day that the samples were run, you can always take that into account in your experiment.
So just a few final words then. Me personally, this was hugely beneficial for me. As a basic researcher who often needs to be reminded on how important this is. It's not as trivial as we think, and we'd like to thank Kevin personally for his time. He did a lot of work putting this together, his expertise, and this information, I promise, will soon be available on the website. We'll send you a link.
Yeah, so again, yes, thank you very much, Kevin. Your time was much appreciated, and I can already see as people are presenting things, the inclusion of better statistics, and at least people are thinking about what they're presenting, which is the whole point. So kudos to you for actually affecting change. As I get around to it, Josie and I have time, we're going to just put a little seminar or survey together to get your feedback. Not only useful for us the next time we have to think about these kinds of things, but also for Kevin. He's in his training still. So any help that you can, feedback you can give him will be useful as well. So we'll send you a link, and it won't take much of your time, but we would appreciate that you fill it out so that we can help improve ourselves and give you what you need.
So thank you for your time, for contributing, and let's all thank Kevin.